All right, welcome back. This is CS4510, L17B, and the topic is completeness within PSPACE. PSPACE-completeness. So PSPACE is a very interesting class in the sense that, I mean, it's about space, but is it really? It's kind of is the point today. So we recall we have a relationship between P and NP. We have P goes here, and then NP goes here, right? And we know that P is a subset of NP by the generalization of non-determinism. We also have a definition of a verifier, and we can just say the verifier, which ignores its witness and solves a problem, also is a polynomial algorithm. PSPACE goes here. It's like big. Right. Pop quiz. Why is what is the definition of PSPACE? How do I define PSPACE? PSPACE is equal to polynomial space. This is the union for k equals 0 to infinity of space. Probably should have done this last lecture. Space of n to the k. Right? Similarly for n space. And we know by Savage's theorem they're equal. Pop quiz. Why is NP contained in PSPACE? There are at least 4 proofs we can come up with. Give me any reason that NP is in PSPACE.
Didn't we just show as well how
What did we just show?
we showed empty space is in P space?
Correct.
They're equal?
Yeah, exactly. PSPACE equals NP space. So why does it tell you NP is in NP space? Why does it tell you NP is in P space?
NP is in NP space.
Yeah, here's the first proof. NP is in NP space, which is equal to P space, okay? That requires Savage's theorem. What's another reason that NP is in P space? Recall NP has 2 definitions, of verifier and of non-deterministic machine. PSPACE is deterministic machines with a space bound, polynomial space bound. So why is NP in PSPACE? Give me another reason.
Can I just brute force the verifier?
Brute force the verifier. Every time you try a witness, you erase it and retry another witness, okay? The witness is at most polynomial length, right? So you brute force search for a polynomial witness over and over, reusing the space. Eventually, if it exists, you'll find it. So if you find it, done. Polynomial space bound. So brute force search for witness. That is a polynomial space algorithm for the verifiable language. Done. What's the third reason? So we can find this one. What is the space complexity of a problem that solves SAT?
The size of the CNF?
Yeah, basically. So if I ask you to decide SAT deterministically, describe the algorithm that would do so.
It would brute force all possible variables, values.
How much time and how much space does that take?
Space, you just need enough space for each configuration at a time, and time is, it would be huge.
Yeah, it'd be like exponential time, but rewriting the assignment could take only linear space, if that's the size of the assignment. So every time you try an assignment, you erase it and write it again. Erase it and write it again. Write another one, right? 0, 0, 0. Okay, that didn't work, 0, 0, 1. That didn't work, 0, 1, 0, and so on, right? That's linear space. So in fact, SAT is linear space. But what do we know about SAT? So we know that SAT is NP complete, so SAT goes here, right? So we know that for all A in NP, there's a polynomial time reduction from A to SAT. And because we also just described why SAT takes linear space, SAT is in P space. Since SAT is in P space, wherever goes the complete problem goes the whole class, if that class is closed under polynomial time reduction. So here is the proof that all of NP can be done in P space. Take the P space machine, it will simulate the NP machine as follows for each language. Compute the reduction, brute force search for the assignment. So take the machine, convert it to a CNF, and then brute force search the CNF. If the CNF has a satisfying assignment, you accept. If it doesn't, you reject. Computing the reduction takes polynomial time. Brute force searching for the witness takes polynomial space. So for each polynomial time non-deterministic machine, there is a polynomial space machine, deterministic one, that does the same problem. But that machine uses the reduction to do it, right? So wherever goes the problem goes the entire class. Okay. What else? Those are basic. I think those are the most important ones, right? And that's an important thing to note about completeness. Like wherever you can place that problem, you can place the class, as long as whatever machine is there is allowed to compute the reduction as well. Why are we talking about completeness today? Well, it turns out that there is this other thing here that is called P-space completeness. And there's going to be a problem here we'll talk about, which is called TQBF, which is basically a generalization of NP completeness. So NP completeness, there's 60,000 problems that are NP complete. It turns out that there's a larger class, perhaps. We don't know if NP equals P-space, by the way. We don't know anything. We don't know if P equals NP. We don't know if NP equals P-space. And we definitely don't know if P equals P-space. Because if P equals P-space, then P equals NP, right? We have no idea of how any of those work. But the P versus P-space question is as hard of a question as the P versus NP question for this reason. It turns out there's a whole theory of P-space completeness with similar but different problems. And that's basically the point of today's lecture, is kind of to talk about how they look. If you had to talk about NP completeness, we say that SAT is NP complete because every problem in NP can be reduced to SAT, and also that SAT is in NP, right? If you had to guess what a definition of P-space completeness is, what would you say it is? Let's say, I'll say TQBF is P-space complete. Since what must be true, if in the most basic, in an atomic way.
It's not an NP.
We don't know that. If it was, in fact, we'll argue later, like if it was an NP, that would imply P-space equals NP. I guess what I'm asking is like the definition of NP hard and in NP is what makes the problem NP complete. So the definition of P-space complete should just be the same thing, but for P-space. We can put this problem, which we'll talk about soon, in P-space, and also for all A in P-space, we can reduce from A to TQBF. That's what we'll do today. Okay. So a problem is NP hard if all problems can be reduced to it from NP. And it's NP complete if it's NP hard and in NP, right? A problem is P-space complete if it's P-space, in P-space, and P-space hard. It's in P-space and it's P-space hard if every problem in P-space can be reduced to it. So if both those things are true, then congrats, you have a P-space complete problem. We don't know if P-space equals NP, and if it was the case, maybe these are all equal to each other. But either way, this is the definition of P-space complete, right? First thing you should ask is, why do we use a polynomial time reduction here and not some other kind of reduction? P-space is bigger than NP, right? It makes sense to use NP reductions here, but why here? The answer is you always want a definition of reduction that is easier than a definition than the algorithm class. You don't want to allow the reduction to do things like brute force search. So you always want a limited kind of reduction, but you want a reasonably limited kind of reduction. There are other weaker reductions. There's, for example, a logarithmic space reduction, too weak. That's for completeness, in fact, within P. You could have an exponential time reduction would be too much. So why not use, and polynomial space, P-space is closed under this anyway, so why not just keep it, kind of the attitude. There was a book I was reading, and the appendix had 13 different definitions of reduction. There's 13 different kinds of reduction. Of course, we learned about the mapping reduction and the polynomial time reduction, but I'll tell you there's a Cook reduction, there's a Karp reduction, there's a Levin reduction, there's a parsimonious reduction, there's a truth table reduction, there's a log space reduction. Each one is used in increasingly obscure ways. So there's a whole zoo out there about how you can express translation of hardness of problems. Polynomial time reduction is the best one. This is, in fact, the CARP reduction, so we'll just keep it. Right, so what is TQBF? As you may understand, P-space to be a generalization of NP, or you may not understand that, it is the case that P-space is a generalization of NP. Even though it's a space thing, TQBF is in fact a simple generalization of SAT. So what is SAT? When you have a formula of the form like X or Y, or Z, and not Z or Y, not something like this, right? You have Boolean formula like this. We say a formula is satisfiable when what happens? When is a formula satisfiable?
When you can verify it and that it return, or not when you can verify it, but it's satisfiable if there exists
There exists.
a solution.
There exists. Every Boolean formula is secretly a logical formula. So we have hidden from you part of the notation because not because we're lazy, but that's where the generalization will come in. This is not technically a Boolean formula, it's technically a logical formula. Why do I say that? There exists X, there exists Y, and there exists Z, such that this is true. There's exists that were in the front of every SAT formula, every CNF, we just simply did not write it. Now, how are we going to generalize TQBF from SAT? SAT is the special case of TQBF, which only has existential quantification. When you allow universal quantification, that's TQBF. That would be an example of TQBF. TQBF stands for true, quantified, Boolean formula. So they are quantified in the sense that some of the they're basically CNFs, but we want some of them to be evaluated for all and some of them to be evaluated for exists. If they're all exist, then it's just SAT, but some of them are for all. By the way, you guys know that quantifiers can permute, true or false?
You mean like rearranged the order?
False. Why? Why?
For all X, there exists a Y is different from there exists a Y for all X.
Let's just do the example. For all X, suppose that for every X there is a Y of X or Y and not X or not Y. And let's do the reverse of there is a Y for all X such that X or Y and not X or not Y. Okay, same formula. Let's swap the quantifiers. What do these two say? And this is kind of a 2050 level thing, right? For every X there is a Y means that every X has a Y. But it also could mean that every X could have a different Y. Just that every X does have a Y. The reverse means there is some Y such that for every X. So what this really, in English, would mean like some Y has every X, which is different than every X possibly having a different Y. Either way, one of these would be in TQBF, and one of these would not be in TQBF. Which one would that be? Let's just determine which of these are true and which of these are not. I claim one of them is true and one of them is not true.
You guys would assume the top one is true?
Why is the top one true?
Well, you said one of them is true, the other is not, and then the top one's less strict.
I guess in a simpler way though, like why is the top one true? Not just that. Well, let's just do it. For all X, there is a Y. So try X is 0. Let's do X0 and X1. If X is 0, that's good. Is that good? No, but there is a Y. Y is 1, so this is good. Okay, so for 0 it's good. For 1 is it good? If X is 1, that's good, but then that's not. So set Y to be 0. So for all X, there is a Y. In fact, the opposite Y. If X is 0, there is a 1. If X is 1, there is a 0. So for all X, there is a Y. So this we would say is an element of TQBF, which TQBF is the set of true quantified Boolean formula. Just to write that. So Q1, X1, to Qn xn of phi of x1 to xn. And then this is true. Right. It's an encoded formula with the what the quantifiers are, where Q1, Q2, for example, are symbols of for all or existence. Okay, so this one is in TQBF. Is this one in TQBF? Let's try to figure it out. Is there a y for all x? Okay, we'll try it. Let's see it. Try y is 0. Is it true for all x? No, because if x is 0, this is false. So try y is 1. Is this true for all x? No, because if x is 1, this is false. Right? That's, in fact, that's a way to rewrite a proof by contradiction. Assume to the contrary there is a y, but here for each y there is a counterexample of x, right? In fact, that's the negation of the statement. For all y there is an x. But it's fine. This would be not in TQBF for that reason. Right. So though that is the definition of TQBF, and we see that TQBF is the generalization of SAT in the universal sense. Questions on the definition of TQBF? And it is not the case that there exists a satisfying assignment, but up to how the quantifiers are defined, the formula is true or not true, right? So we want to first prove that TQBF is in PSPACE. How do you prove a problem is in PSPACE? PSPACE.
You prove it can be done in polynomial space.
Exactly. And how do you do that?
You can just show the existence of some algorithm that can compute it.
Exactly. Every theorem is really an algorithm. So we're just going to give an algorithm for a TQBF, and then that's going to, we'll be like, yep, that's polynomial space, and that's sufficient to prove that it's in PSPACE. So the algorithm is basically going to be divide and conquer. Okay, so we could brute force search, and that's fine because we don't care about time complexity, but we do care about space complexity. So unlike where we could easily say, oh, SAT, rewrite the thing, here we can't do that because there's non-existential portions of the formula. There's universal ones. So we need a little smarter way to keep track of information and still make sure that we only use polynomial space. And the answer is we're basically going to do a divide and conquer algorithm that is identical to Savage. So let us suppose we have an algorithm A, which takes as input a TQBF of Q1 x1 to Qn xn of phi of x1 to xn of this form. It's encoded like this, right? And we want to solve such a problem recursively. Now, if there is no quantifiers, what should we do? If no quantifiers, just evaluate and return appropriately. There's no quantifiers, there's no free variables, so there's just a bunch of constants there, ones and zeros, that you just are going to and and or together in return. So that's going to be your base case. Else, we can say if, let's say, Q1 is equal to the exist statement. If Q1 is equal to the exist statement, then we know that exists x1. So the formula, if it's true, is true either for x1 is 0 or x1 is 1. So what are we going to do is just recursively try both and return if one of those accepts, right? Return A on input, Q2, x2, Qn, xn, phi of 0, xn. That's like four different parentheses. Or A on, maybe I write it underneath. Q2, x2, Qn, xn, phi of 1, xn. if x exists, one of these recursive calls will return true, okay? If Q1 is universal, what should we do then?
You have to return the same thing, but and.
Please don't make me write it. Okay. Do we agree? It's typeset in the notes, okay? Do we agree that this is an algorithm for TQBF? Okay. If there exists an x, try plug in x equals 0 and x equals 1, recursively call that, and if it exists, it'll return. Now, if it must be for all x, then make sure both of these recursive calls return true, right? It's important to remember that TQBF quantifies over a Boolean only. It cannot quantify over, for example, a string or something like this. It must be a single bit, right? It turns out that won't be too problematic for us. That'll be okay. Either way, this is an algorithm for TQBF. Before we get into the analysis, do we agree that it solves TQBF? Okay, what is the space complexity of it? Recursive calls are going to be reused. So what is the depth of the recursion?
Log n.
Not necessarily. This one is too simple in that way. Instead of dividing the input by 2 over and over, the recursion here just knocks off a quantifier, right, over and over. So what would the depth be?
N.
Yeah. How much space is used at each level?
The same amount.
Yeah, honestly, like it's all in the stack frame anyway, which is just the size of the formula, which we can basically ignore because that's part of the input. So we can just like, obviously without getting too deeper into that, we could say it's probably, it's really the depth of the recursion, which is linear. So we see that TQBF is not only polynomial space, but linear space. So this is a linear space algorithm for TQBF. Now, what is the runtime of it? This is not important, this is a space complexity lecture, but if I asked you about the time, what would you say? This is a tough question.
Can't remember.
Yeah, so I would say like it's exponential time. Every configuration is eventually tried. So like in the recursion tree, each leaf is some assignment of zeros and ones, okay? So every configuration exists somewhere in the tree. But it's organized in such a way so that you can keep track of the for alls that exist and how they relate to each other. That's sort of what's important here. Either way, each assignment is tried, and there's exponentially many assignments, so it takes at least exponential time. We do not expect to not have this. By the way, if we're trying to prove TQBF is p-space complete, what would be the consequences if we had a polynomial time algorithm for TQBF?
It would be an NP.
Simpler than that. It would be in NP. If TQBF was in P, then p-space would be in P as well. But we already know that NP is in p-space, so that would imply that NP equals NP. So another reason we don't believe P equals NP, if you could prove TQBF was in P, you could get P equals NP for free. Forget NP. NP is not even mentioned. It's just like a very trivial connection to a connection to a connection kind of thing. A space complexity question implies a time complexity one, right? A space complexity question implies a non-deterministic question. So you should take this as evidence as you probably can't improve this to be polynomial time. Fine. It's good enough. be happy with that and just leave it alone, right? So, questions on proving that TQBF is in PSPACE? Okay, we need to prove it's PSPACE hard. The way we will do that is we'll do 3 bad proofs and then slowly improve each one until we get to the right one. We want to prove that for all L in PSPACE, there is a polynomial time reduction from L to TQBF. You recall how we did Cook-Levin, right? When we did Cook-Levin, we did for all L in NP, there was a reduction from L to SAT. And the way we did that is that we said the non-deterministic machine on W accepts if and only if some formula phi with hard-coded N comma W and then T was in SAT, right? We made sure that a formula was accepting if and only if and we made sure that the CNF had an accepting assignment, had a satisfying assignment if and only if the machine accepted, right? So why don't we try the same thing here? Let's suppose we have a D on W accepts using, let's say, S of N space. Could it be the case that we make that true if and only if some TQBF accepts? Sorry, is true? Could it be the case that we just apply Cook-Levin? Let's think about it. Does Cook-Levin just give us this theorem for free? So if we recall how we did Cook-Levin, we did this table and then we made sure that the input to the formula was provided via a configuration that existed in the non-deterministic machine. Let's suppose we were to repeat the thing with a space-bounded machine. It's deterministic though. So the width of such a table would be that big. And the height would be something like this though. So the width of the table would be approximately what? Does anyone remember?
It was the size of each configuration.
Exactly. How big is this configuration of a space-bounded machine?
The space complexity.
Yeah. S of n. So the table here would be S of n. The width of the table would be S of n. Well, what would the depth of the table be?
2 to the S of n.
Yeah, let's just say 2 to the O of S of n. So the size of the table would be S of n times 2 to the O of S of n. Okay? Now, if S of n is a polynomial, because this is a polynomial space machine, the reduction must write down this table in polynomial time. It cannot be done. So Cook-Levin doesn't work. Okay? We cannot just throw Cook-Levin techniques at it and immediately get it for free. Problem. Also, this is not even a good scale representative of how big this is. This is just 3 times the height, the depth is 3 times the width. It should be exponentially many more times the width. So it's more like this, right? Something like that. And then Cook-Levin, it was like polynomial time. NP was like that big, and that's like PSPACE, right? Anyway, this is too big. This is not a polynomial. So a polynomial time reduction won't succeed. It won't have enough time to even write down the table. Okay, problematic. The second problematic thing is that Cook-Levin also only used existential quantifiers. We have existential and universal quantifiers. So we can write down a formula that takes advantage of both. The Cook-Levin reduction could never do such a thing. We can, right? So we're gonna do that thing right now. So this was the first failed proof. Let's do a second proof and then we'll improve upon it. There will be another problem with this proof. So we can just kind of try Savage's theorem, which is that let us define first a base case configuration. We want a quantified CNF, which consists of CI, CJ, and then T. And we want this to be in TQBF if you can go from Ci to Cj in t steps, right? We would like such a quantified formula to be true if that is the case. Then the construction is simple. But what about, let's say, in the base case, how would we do Ci, Cj1?
We just run A.
So this specifically must be a bunch of ands, ors, nots, CNF styled, maybe some universals, maybe some existentials. But I would like a formula to be true if and only if, in one step, you can use Ci to Cj. And this has some input as well, which is the encodings of those and so on.
I would do CNF of the form CI and the delta function. And if that produces CJ, then it returns true.
Basically, I'll tell you the way the literature would say this. By a procedure similar to the Cook-Levin theorem, we can construct a Boolean formula such that this is satisfiable. And the CNF would be basically, instead of a table, we would do a 2 by n S of n table, right? This would be 2, this would be S of n, because it's the size of the configuration. CI would be encoded here, CJ would be encoded here, and you just check that a couple checks. What do you check? Some basic stuff. You do like the 2 by 3 legal windows, all that other stuff. Whatever that is, this is like efficient size, right? What is the size of such a formula?
2 to the S of n. Or sorry,
It's
2 times.
Yeah, maybe like 2 times S of n. So, in fact, naively, for surprising reasons, this is approximately O of S squared of n. It is very difficult, and so basically what happened is, every book says this is polynomial in S of n, okay? They either say polynomial in n or poly in S of n, and they give up. They're like, we're not gonna figure it out. That's probably good enough. There's one book, the Aurora Barak book, it's the most modern book, says just straight up linear, which is actually very plausible because it's just the size of the table. But then no one could figure it out, the actual thing. So we were convinced it was an error. Actually, I was fully convinced it was an error. And then a student came up with a formula, and it's very, very complicated. And it chains together windows in a linear fashion that allows you to check certain things. And it probably is S of n, and not S of n squared. But naively just consider it as whatever, it doesn't matter, polynomial. Okay, base case done. Now I'll tell you how we're gonna define phi of C, this is called S of x, right? Ci, C, J, and T. We'll define this to be basically using the Savage's theorem recursion. We will define a CNF recursively on top of other CNFs. So what we know is that this is true when Ci to C can be reached in T over 2 steps, and you can go from C to Cj in T over 2 steps, right? But how do you find the C for this? What you do is you just existentially quantify over it. There exists a C such that you can go from Ci to C in T over 2 steps, and then C to Cj in T over 2 steps. Now, when I write this big exists C here, note that this is a sequence of exists. This is actually exists, right? It's an encoding of some Booleans that really are the configuration in binary or something, right? However it's done, that's what's going on there. But let's just, for shorthand, just do a giant big exists, but that's what's going on. Now this almost works. There's another problem with this. What's the size of the formula? And this is difficult to analyze. Every time, so the recursion depth, quote unquote, would be what?
Log T.
Yeah, so every time time t halves, the formula doubles in size. Right? How many times is the formula half? Log t times. But every time it'd be log t doubling the formula over and over, So here there's 2, the next one would be 4, 8, 16, and so on. So you're gonna get a really big formula. And approximately what is that gonna be? If t is the time, and you know, it's gonna be log t here. Log t is gonna be log of 2 to the O of S of n again, right? Which just makes this S of n. But every time it does so, it doubles whatever the base case is, right? So this is going to be something analogous to like 2 to the O of S of n. It's smaller than the previous one, but it's still too big, right? So that's not good. But there's another thing that we still haven't used as a universal quantifier. So, hello, welcome back. This is now the afternoon. I realized the video did not save. So I just went ahead, well, the last 15 minutes-ish, 20 minutes-ish of the video did not save. We just went ahead and finished the lecture to the students. They asked many good questions. So I'm gonna re-record the last 10, 20 minutes of this and try to remember the questions they asked me, and we'll just get it done. Last thing we talked about was that there was some true quantified Boolean formula phi for CI/CJ1 that was in TQBF if and only if CI yields CJ via delta in one step. And we argued such a statement was true by the Cook-Levin theorem. Essentially, you could make a little tableau here of size 2 by S of n, and this was approximately Pauli in S of n. Whatever that is, it's small, maybe S of n squared. Then we said that in the general case, you can say by a recurrence similar to Savage that CI/CJT can be said to be, there exists C of some phi of CIC T over 2 and CJ T over 2. And we said that this exists C here is actually exists. It encodes several bits. TQBF is you're quantifying over Booleans. It's a true quantified Boolean formula. And we said such a recurrence was fine. The number of times this recurrence occurs is the number of times you can divide t by 2, and then when you solve for that bottoming out, you get that this is log t depth, same in Savage's theorem. And for t, the time of the machine, when we know that it has an S of n space bound, we know that this is approximately t is 2 to the O of S of n. So we know that this is like S of n recursion depth. So if S of n is polynomial, that doesn't sound bad, but every time you divide t by 2, the formula doubles. So that's really like every time divide t by 2. So this is kind of like 2 to the Pauli of S of n, something like this, something big and ugly. And although that may improve upon the naive Cook-Levin implementation, that's not that good. So what can we do about this is, although this is, again, we're doing the fact that TQBF is PSPACE complete. We did the Cook-Levin idea, which argued, okay, well, that's not going to immediately work. We said, okay, well, let's shrink it a little bit using quantification to kind of do intermediary steps for us. That works a little better, but not much. So we can, in fact, improve upon this even further by the use of the universal quantifier. So again, exists C of phi of CI, C T over 2, and phi of C, CJ, T over 2. This doubles every time you recursively subdivide the formula. So what we can do is actually use a universal quantifier to quote-unquote recursively fold the formula in half instead of having it double. What is an and if not a for all? So what we can simply say is, analogously, there exists C for all Z, where Z again is not one thing but an encoding of several Booleans, where in fact it's either the case that Z is equal to a CIC or Z is equal to CCJ, and whichever one it is, that implies phi of z t over 2. Now z here again is an encoding of two configurations of the machine, and notice that basically for all z here, it's this one or this one. This corresponds to the case that it's this one, and this corresponds to the case that it's that one. And whichever case it is, it must be the case that z being that implies that. Now, some other things. First off, this implication is not valid CNF notation, but that's fine. You could believe that you could go by conditional disjunctive equivalence. P implies Q is equivalent to not P or Q. Number two, why is this formula smaller? So first off, this is going to half and half and half again. So every time t halves, what happens to the size of the formula? Approximately this thing gets added in front, right? So it would be exists C for all Z, this implies, and then this would be some exists C prime for all Z prime, and then there would be some other formula, T over 4, and so on, right? And that would repeat over and over until we got to some base case out. But doing it this way, we get something very nice. Every time T halves, we add this. What is the size of this object? Well, there's some configurations there. That's approximately O, the size of a configuration, which is the, it's 4 times the size of a configuration, in fact, which is the space bound. So this would be the formula increases by size O of S of n, right? So we can deduce that the size of the formula is going to be S of n plus S of n plus S of n plus S of n for each time you divide t by 2. And every time, the number of times you can divide t by 2 is again going to be log t, which is going to be O of S of n. Plus this base case. So this is going to be poly in S of n anyway. So it's the base case plus S of n, S of n. So that's going to be, of course, poly S of n. Either way, we see that this is a polynomial size formula. It's a little more cumbersome and complicated, but importantly, it uses this universal quantifier in the way that the two previous ones could not. We see that this is sufficient for us to prove that for every language, L in PSPACE, there's a polynomial time reduction from L to TQBF, where this true quantified Boolean formula, cumbersome to construct, the polynomial time reduction, you can still write it down. It converts the polynomial space machine and the input W and even the time bound T to this Boolean formula, such that the formula is true if and only if the machine accepted W. So we see that there's a direct reduction from L to TQBF, and that's sufficient for us to say that L is PSPACE hard. That would complete the proof. Now, why do we care about PSPACE completeness? One student mentioned, isn't PSPACE completeness kind of useless? Kind of. Let's get to that. We have P here. We then have NP here. And we know that there are the hardest problems in NP, which are NP complete. And we know certain problems to be NP complete, such as SAT, clique, 3-coloring, vertex cover, knapsack. But interesting to note is that several other puzzles are also NP complete. In certain formalizations, we have Minesweeper, some kinds of Tetris problems. I have Sudoku, Rubik's Cubes in some specialization are NP complete. But then we know by the previous 4 proofs we did that NP is contained in PSPACE. This is a terrible circle. This is PSPACE. Oh God, I'm ashamed of this. Okay. And we know that there are the hardest problems in PSPACE, which are, now we know is TQBF goes here. But importantly, there are many things that are also PSPACE complete. And we're not going to actually do a reduction the way we would have done a reduction for in 3510 we do a zoo of reductions here, 10,000 reductions. There's like 100 problems probably, less known to be PSPACE complete, but among them I'll tell you these are chess, and I gotta be careful, it's chess if there's a polynomial depth to the number of moves in the game. By the way, every time you say something like this is NP complete, or it's under a decision formalization, and you have to be very careful. It is the case that chess is PSPACE complete. First off, you have to generalize chess. It's not an 8x8 game, but an n-by-n game. And it is the case that the decision problem is, given a specific instance, is, for example, white winning. That is the decision variant of chess. And if you say the depth of the game, the number of moves of the game is bounded by a polynomial of the function of the size of the board, only then is it PSPACE complete. And with similar restrictions and generalizations, we have checkers, Go, reversey. Is that right? It's reversey? Let's just not say that I have that. Mahjong. Again, these all need to be decisionified and generalized to n-by-n boards, and then also into yes or no questions. Any two-player game of perfect information. Perfect information basically means both players know where everything is. For example, Battleship is not a game of perfect information. And in most MOBAs and most, like, I guess, first-person shooters and these kinds of games, Civilization is a game not of perfect information. It's a game of not perfect information is when part of the map is shadowed. One player knows, they know different sets of information. A game of perfect information is like chess. Everyone knows where everything is, you know, and the strategy doesn't come from any lack of information. Interesting to note that what is NP complete is a lot of puzzles. And what is a puzzle if not, can I spell that? A puzzle, what is complete? A lot of puzzles happen to be NP complete, and a lot of games have to be PSPACE complete. Why is it the case? Well, consider the difference between SAT and TQPF. In SAT, you make a sequence of decisions, and then somehow the rules of the game are encoded, the game, quote unquote, the puzzle, are encoded as a CNF. You choose a move, then you choose another move, then you choose another move, and then you choose another move. This is exactly what makes the whole witness thing and the verifiability condition, right? You can convince someone of an answer for the same reason that you were the one making all the moves. First, for example, you place a Tetris piece, and then you place another Tetris piece, and then you place another Tetris piece. In contrast, a lot of games are PSPACE complete because of the difference that TQPF makes. In a sequence of alternating quantifiers, it's as if you moved, then your opponent got to make a move. For all possible moves your opponent could make, you must take those in consideration. Then you make a move, and then for any move your opponent make, and so on. The universal quantifiers, in an alternating fashion, encode in a possible opponent's move. Even in some sense, they could encode, for example, a random move. There's this notion of like games against nature done by Papa Dimitriou, where perhaps you're not playing against someone, but you're playing against a random choice. Even in such formalizations where the for all does not capture an adversarial choice, but a random choice, these things are still PSPACE complete, right? An example of that would maybe like you're in the stock market or the weather or something like this, right? But either way, the universal quantifiers are encoding basically like opponent moves, and the existential quantifiers essentially encode your moves. So under that framework, a lot of games happen to be PSPACE complete and not NP complete, and a lot of puzzles happen to be NP complete. What is a puzzle, if not a single player game? What's the point of this then? So what's the point of PSPACE completeness? Under strong complexity, reasonable complexity assumptions, if NP does not equal PSPACE, then we could say that games are harder than puzzles. Now, that's a cute little byline in a news article, and I guess it kind of makes sense, but does it really? What's really the difference between NP and PSPACE? It's as if there are at least three notions of exponential time, right? So we have NP is a subset of PSPACE, which is a subset for some obvious reasons of why every polynomial space machine takes exponential time, deterministic, right? So these are, but to an algorithm designer, they would not care about this at all, honestly. NP, these are really three different ways to think about exponential time. NP is exponential time, but easy in the sense that the computation is at least verifiable. PSPACE is exponential time in the sense that there's at least polynomial in the amount of bits used on the tape. And exponential time is actually exponential time in the sense that it has neither of those two easiness restrictions. But really, all these contain languages that are exponential time. And in some sense, people think of NP as XP anyway, which is incorrect, and you shouldn't think of this. NP is at least easy enough to verify, but so to an algorithms designer, there's really no difference between NP and PSPACE. But to a complexity theorist, because we have this distinction between them, we can say something about the difference between games and puzzle. Now, what do you think the best algorithm for SAT is? The best algorithm we have for SAT is brute force search, 2 to the n, in the sense that you try all 2 to the n rows of this truth table. In fact, we don't have anything how to beat this. What about TQBF? What's the best algorithm for TQBF? It turns out it's actually not, it's slightly faster. It's 2 to the 0.77n, something like this. It uses some dynamic programming or something like this, right? Which is kind of surprising that it sounds like TQBF is faster than SAT, but that doesn't make sense because SAT is really a special case of TQBF. The reason that works is in SAT you measure this basically in the number of variables, so exists. But for TQBF, it's as if it's an alternating formula, so it's as if only half of them are existential, the other half is universal. And so in some sense, there's just half as many quantifiers in the way that it's measured. Either way, this is what we get. All right, let's see if I can remember what the students' questions were. There was a student question about the distinction between these three, because really, to an algorithm designer, they're kind of useless. And I guess proving something to be PSPACE hard is useful in the sense that under the assumption that under the assumption that NP does not equal PSPACE, then proving a problem to be PSPACE hard means that it's probably not an NP, and therefore probably not even verifiable, in the sense that you shouldn't expect to be able to verify the solution to the problem. It can also mean that it being PSPACE hard probably means it's not in P, because if a PSPACE hard problem was in P, like such as for example, if TQBF was found to be in P, that would imply P equals PSPACE, which, fun fact, NP is between those two, so if PSPACE equals P, if any PSPACE hard problem gets into P, P goes under polynomial stem reduction, where it goes a PSPACE hard problem goes the entire class of P. So this would go the entire class of PSPACE, excuse me. So you could put all of PSPACE in P, which would mean P equals PSPACE, which is also equal to NP. So for that reason, for example, if TQBF were to be in P, P would equal NP. But we don't believe this to be the case. So that's another piece of evidence you can think about it being PSPACE hard. And this is probably not NP hard, because if you could efficiently verify TQBF, then PSPACE equals NP, and there are consequences to that as well, which we don't believe to occur. So some of it is with certainty, and some of it is with this chain of implications that, oh, we don't believe this to happen, so that probably can't happen, back and forth. I think that's everything I can probably say about PSPACE completeness. You'll very rarely come across it in nature, in the sense that there are 60,000 NP complete problems. They show up all the time. There are these are the only PSPACE hard problems I can think of. I can't think of many other PSPACE hard problems. Okay, I'm gonna go edit this together.